Good morning, chemistry class. Welcome to, I don't know, happy snow day. All I'm saying is, whoever made Elsa mad to bring on the snowstorm, stop! I'm just kidding, it's fine. I like snow, it's fun. So, we are going to go through our next chapter, or our next section chapter. So, this is a video that's going to go through our PowerPoint. So, here we go. And yes, if you listen carefully, you can hear Cocomelon in the background because uh, there's a child back there somewhere. Say hi, Molly. That's all we get. Anyway, let's jump into it and let's do some chemistry. So, as a quick review, our last section was kind of about the atom and the different pieces of the atom. So remember, we've got protons, which are positive, electrons, which are negative, and neutrons, which are neutral. Get it? Neutrons, neutral. Never mind. Anyway, so remember, inside of the nucleus, you've got your protons and neutrons, and then your electrons are kind of flying around around the outside. And so we went over several different kinds of experiments and how they kind of figured that stuff out. So I encourage you to review that if you need to. I can promise you that those different names of scientists are going to be things to remember. And those are things that I forget all the time anyway. So that would be something that I would have to study. Anyway, so 4.3, how atoms differ. So remember, this is kind of a sticking point on that quiz. Dalton said that all atoms of the same element are the exact same. So that is actually not true because we have these things called isotopes right here. We're going to learn a little bit more about those. So section 4.3, how atoms differ. We're going to explain the role of atomic number in determining the identity of an atom. We're going to define an isotope, and we're going to explain why atomic masses are not whole numbers. And then we're going to calculate numbers of electrons, protons, and neutrons in an atom given its mass number and atomic number. I wonder if there's going to be a worksheet about that. It's weird. So remember, the periodic table is that chart that organizes all of our elements. Again, remember, I will not ever ask you to memorize the periodic table, but it's something to be familiar with. So again, if you don't have the app or anything like that, you should. And we're going to go over all of these words here momentarily. So the main idea is the number of protons and the mass number is define the type of atom. So the number of protons and the mass number define the type of atom. Okay, here we go. So the atomic number, each element contains a unique positive charge in their nucleus. And that's kind of how we define the different elements. So for example, if you were to look at the periodic table or on your app or whatever, you will have something that looks like this. Now, they all kind of differ a little bit, but they all have typically the same type of information. So we've got the atomic number, which is right here, which is the amount of protons. So atomic number, amount of protons. So that's located right here. It's a whole number written on each square of the periodic table. And this really defines which element you're talking about. And of course, there's the name and the chemical symbol here. Your apps might just have the chemical symbol and you tap on it and then it'll tell you, the name of it or whatever. But then you also have this number down here. This is called the average atomic mass. So we're going to talk more about that in a little bit, but know that this is the average atomic mass, and most importantly, this is the atomic number right here. So remember that part. So I mentioned that that there was an average atomic mass. So all atoms of a particular element have the same number of protons and electrons, but the number of neutrons in the nucleus can differ. And that's where that average atomic mass comes from. So atoms with the same number of protons but different number of neutrons are called isotopes. So this is the big thing that Dalton kind of got wrong. To his credit, he was way before his time, but whatever. Is that you can have two hydrogen atoms with different masses, and those are called isotopes because they have a different number of neutrons in the nucleus. And that's where this word comes from. That's what we're talking about. So the relative abundance of each isotope is usually constant. Isotopes containing more neutrons have a greater mass. That kind of makes sense. And isotopes have the same chemical behavior. And so, again, if we're using that hydrogen example, a hydrogen atom is a hydrogen atom. It's going to act like a hydrogen atom. But some of them can still have more neutrons than others. So the mass number is the sum of protons and neutrons in the nucleus. This is specific to each isotope. So like if you have an isotope, that isotope has a specific mass number. This is not the average atomic mass that you find in the periodic table. But this is specific to, here is a specific isotope, its mass number is blank. From that, you can then figure out the number of protons and neutrons in the nucleus. So, for example, my face is just getting in the way. Ah! I'm sinking! I'm sinking! Whatever. So, for example, we've got potassium, and we've got 3 different isotopes of potassium. So we've got potassium 39, potassium 40, and potassium 41. So these are the atomic number for each specific isotope. So here's a pictorial representation of each potassium. And notice how each potassium has 19 protons. That is its atomic number that is located on the periodic table. But the neutrons here differs. So there's 20, 21, 22. And then the electrons are going to be the same as well. So for now, until we get into later on in the semester, the number of protons and electrons are equal. They're always equal for now. Later on, when we start to have electron sharing and electrons going whatever, then charges might change. But for now, just assume that protons and electrons are the same. So, if we have potassium 39, you can look on the periodic table and you'll see that potassium has the atomic number of 19. So then, if you just take 39 minus 19, you will have the number of neutrons for this specific isotope. So remember, you're using the atomic number that is the whole number on the periodic table, not the atomic mass. So our little pictorial example, I guess I could count these, but I think the blue ones are protons and maybe the orange ones are neutrons. I don't know. You'd have to count it, but whatever. So the inside of this nucleus here, you're going to have 19 protons and 20 neutrons. Inside of this one, this is a bigger isotope. You're going to have 19 protons, 21 neutrons. And then this one, it's even bigger, 19 protons, 22 neutrons. So again, protons remains the same. You can find that in the periodic table. And then for a specific isotope, you can figure out how many neutrons you have by taking the atomic mass, or the mass number, minus the protons or electrons, whatever. But this is the number that you get from the periodic table. So one atomic mass unit, AMU, is defined as 1/12 the mass of carbon-12 atom. So I mentioned that earlier that there's that there are some measurements that we literally just took a thing and said, okay, we'll start with this thing and call it a gram, and then we built our system from there. So they did that. Chemistry did the same thing. They took carbon-12, it's a very common atom, and it has very typically 6 protons and 6 neutrons. So then if you add those together, it's 12, and then you divide that by 12, you get about 1 mass of whatever that they wanted to start with. So 1 atomic mass unit, AMU, I'm back, is based on carbon-12. So based on that, 1 AMU is nearly but not exactly equal to 1 proton and 1 neutron. So an electron, here's the mass, proton, here's the number, and neutron, here's the number. So these numbers are not things that you need to memorize. What you do need to remember is that a proton and a neutron equals about 1, and an electron equals about nothing. So it's so small that it does in fact have mass, but it's not a lot of it. So we essentially consider electrons to be massless most of the time. But again, proton and neutron both equals 1. The atomic mass of an element is the weighted average mass of the isotopes of the element. So this is the other number that you see on the periodic table. There's a whole number, that's your atomic number, that's how many protons you have. Then there's the average atomic mass of that element, and that for hydrogen is like 1.00 blah 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 blah, something like that. And that is based on the different isotopes and how common they are. So calculate the weighted average of atomic mass of chlorine. So we've got 2 different isotopes here. We've got chlorine 35, chlorine 37. Notice how they're writing it here. The mass number for this specific isotope is on top. The atomic number is on bottom. So I think you will have to have a worksheet where you write these things out. So I want you to kind of take note of that. So again, can I zoom in? No, I can't zoom in. But the 35 is your mass number for this isotope. The 17 is the atomic number. So we look at the nucleus. We've got 17 protons. We subtract the 2. We've got 18 neutrons. And now we've got some additional information over here. We've got the atomic mass right there. And then we have the percent abundance, 75.78%. So the way we're going to figure this out is the mass contribution. That's what this part is called. You're going to take the atomic mass times the percent abundance. You're going to get a number. And then you're going to add it to the other isotope's number. So again, same information, atomic mass here, percent abundance, mass contribution. Take the mass times the percent equals a number, and you add those up. So that is how they find the total weighted average of the mass of chlorine. So right here. So the reason they do that is this mass right here is much more common. 75% of the time, chlorine is going to appear like this. So it averages heavier, I don't want to say heavier. It averages more common to be this mass. So that's why we times it by the 75%. Now remember, when you're putting that in your calculator, if you have a percent sign, great. If not, you put 0.7578. So remember, percent is 0.7578. So then you get a number, and you add it to this number over here, and you should get a number that is relatively close or in between these two numbers. So if you get a number that's totally off the wall and not anywhere close, you probably did something wrong. Check your math. And again, I'm pretty sure that you will have to do this on some worksheets that I'm about to assign you as well, so take note. Boop. Hey, look at that. We made it to the end. Any questions? No questions? Okay. I have questions for you. An unknown element has 19 protons, 19 electrons, and 3 isotopes with 20, 21, and 22 neutrons. What is the element's atomic number? So I'm giving you a moment to think about it. So there's a lot of information here. 19 protons, 19 electrons, but we're looking for the element's atomic number, so we don't care about the rest of this. So we don't care about the isotopes because the atomic number is going to be the number of protons. So again, right now, you can just assume that protons and electrons are equal, but if for some odd reason they're not, which happens, and we'll talk more about that later in the semester, but protons is always the same. If you change the amount of protons in an element, you are changing the element. Elements with the same number of protons and differing numbers of neutrons are known as what? Well, we can use our testing strategy. Isotopes, maybe. Radioactive, we didn't talk about that at all. Abundant, Ions, we have not talked about at all. That comes later in the semester. So let's go with isotopes. So there we go. You now know stuff about isotopes. Check Canvas. Make sure you are up to date with all of your assignments. I know I'm going to add a little bit more for our E-Day. But other than that, I will see you in class. Have a wonderful snow day. Oh, I was going to hopefully bring my face back up. There I am. Have a wonderful snow day. Bye.